Hi, I'm Fiodar Kazhamiaka. I'm a postdoc working with Matei and Peter, and in this video, I'll be talking about the opportunities and challenges in the development of autonomous vehicle query systems. We exist in a highly dynamic physical world, but knowledge of how it moves is distributed among the billions of inhabitants. Presently, there is no practical way to answer questions such as how many people are currently walking their dogs in San Francisco, or the location of the nearest open parking spot, or how many bicycles crossed Main Street last Tuesday. New mobile sensors, such as those in smartphones and surveillance camera networks, have enabled many applications, but provide limited insight into the world at large. We believe that the next big data platform will be autonomous vehicles. A fleet of vehicles generate data that forms a real-time partial snapshot of the state of the physical world. Now, here are some examples of queries one might ask about the physical world. The first is about the number of people currently in line outside a coffee shop, which can help someone decide when to visit. The second is about a statistic, the frequency of bikes appearing at a particular road crossing, which might be asked by city planners looking for ideal places to install bike lanes. The third is about the location of road debris, which roadway patrol currently answers by relying on travelers to call in. People are already doing these applications at a very limited scale. The new cars are equipped with many high-resolution sweep sensors. The primary purpose of these sensors is to facilitate some level of automation. Currently, that's features like adaptive cruise control and emergency braking, but eventually higher levels of autonomy. We propose a secondary use of autonomous vehicles as a distributed sensory and computing platform, where vehicles upload their data to warehouses or process queries at the edge. The question we ask is what kind of system needs to be in place to support querying? Here, the bulk of the challenges are in the nature of the collected data. Getting answers to queries through autonomous vehicles isn't always straightforward. To start with, autonomous vehicles collect enormous quantities of data, several terabytes per hour, that far exceeds our capacity to transmit and store in entirety. By comparison, Netflix, which represents roughly 15% of worldwide internet traffic, streams the equivalent of approximately only 1 million vehicles. We believe this volume needs to be reduced by 4 or 5 orders of magnitude to be viable. There's also a problem in the way vehicles collect data. Their primary task is transportation, and traffic patterns create a sampling bias in the dataset that can be difficult to account for. Finally, autonomous vehicle query systems are a non-starter unless they can provide guarantees on the privacy of the passengers as well as of the observed individuals. In the rest of this video, I'll discuss these three challenges in greater detail. Starting with data volume. At the scale of terabytes per hour, transmission and storage is very expensive. How do we go about reducing it by 4 or 5 orders of magnitude? We want to reduce volume without sacrificing information content. A key point to note is that a large part of autonomous vehicle observations are of static objects, for which a single record may be enough to answer a query. Most interesting queries are instead on dynamic objects, whose state is likely unknown if not under direct observation. But even for dynamic objects, a single frame can be enough to capture its essence, and the rest of its state can be condensed into low-volume tags describing their location, pose, and other features. We can also take advantage of multiple objects being present in the same frame, which leads to an interesting problem of frame selection. Here, we can carefully select frames that minimize the total number needed to capture all objects. A simple algorithm for doing so, which we describe in the paper, can reduce the number of frames by a factor of 70 to 250 when tested on datasets of driving footage from Palo Alto, Boston, and Singapore. More details on the frame selection algorithms can be found in our paper. The format or representation of the data does not have to be the same format in which it was collected in. Autonomous vehicle data is primarily unstructured and processed by machine learning algorithms to extract information. Recent work looks at building universal embedding networks for vehicle data logs and attribute embeddings to efficiently tag short clips or logs of data with specific set of attributes, such as whether the clip contains observations of a car making a left turn. The product of the two embeddings indicates the presence of attributes within the clips, and the log embedding is an order of magnitude smaller than the original log. One can imagine using a universal embedding network as a sort of autoencoder to compress the data to support historical queries such as Q2. To summarize, there are many opportunities to reduce autonomous vehicle data without sacrificing information content, including frame selection and alternative formats such as embeddings for data storage. The next challenge I'll discuss is data bias. Vehicles use some roads more than others, and at different frequencies over the course of a day, which skews observations both spatially and temporally. Recall Q2, which asks about the presence of bikes at an intersection. We illustrate observations of several vehicles with orange blocks marking times when the target intersection was in view, and their frequency is sketched with the orange line. Bikes, represented as green triangles, will be present in the data more often during some parts of the day than others, but this may not represent their true distribution, sketched with the green line. Some parts of the day had more observations, where it was more likely for bike presence to be recorded. We can account for this discrepancy with importance sampling, which is the process of estimating an unknown distribution using samples drawn from a different distribution. We want to estimate the distribution of bikes using samples obtained from vehicle driving patterns. To account for daily traffic patterns, we can divide this calculation across time intervals, for example, hours. The naive approach would be to estimate the sampling distribution using saved observations. But because we discard data to conserve volume, it is likely that many of the null observations are lost. To recover the true distribution, we need to preserve some record of every location the AV observed. One way to do this, with relatively low storage demand, is to discretize location and track when LiDAR points fall into a segment to determine when it was observed. Here, segment size would determine how specific we can be when specifying location in our queries. Maintaining observation records can enable us to use importance sampling to account for spatiotemporal observation bias even when null observations are discarded. Another problem is the potential for correlation between vehicles and the objects they observe. For example, traffic lights sync the flow of vehicles on the road. When a vehicle stops at a red light, it is joined by other vehicles, which then travel as a pack to the next light. Vehicle data will indicate presence of vehicles at a higher rate than reality after a sync point, such as a traffic light. We have observed this behavior in our experiments with an autonomous vehicle driving simulator. The heat maps indicate the percentage of time a vehicle observed each location, and the percentage of time a bike was observed. Note the distinctly higher percentages in roads around traffic lights. Even with an accurate sampling distribution estimate, importance sampling tended to overestimate the presence of bikes. Shown here is the cumulative fraction of error. In summary, to address bias in autonomous vehicle data, we can maintain a lightweight record of observations to estimate the sampling distribution. The issue of correlated sampling is an open problem. Finally, I'll talk about privacy. As a point of comparison, Google's Street View is perhaps the closest thing to a high-coverage dataset containing visual data. Street View faced a lot of backlash around the potential for privacy violations, which they handled by ensuring that faces and license plates are blurred. Autonomous vehicle query systems can be thought of as an advanced form of Street View. Access to recent and labeled observations makes it all the more important to put privacy at the forefront of design decisions. A well-known study using smartphone location data discovered that it takes only around 4 location points to uniquely identify an individual out of millions of others. If observed individuals can be tracked through autonomous vehicle data across frames, there's a risk of privacy violations. This means that, in addition to blurring faces and license plates, other steps need to be taken to ensure that the query systems aren't used for tracking individuals. For example, any features which can identify an individual over several disjoint frames, such as silhouette, gait, and clothing, need to be obscured. One way to do this might be image segmentation. Autonomous vehicles themselves could be tracked through digital camera fingerprints across multiple frames, which calls for additional image obfuscation or noise without sacrificing image data quality. This kind of processing needs to be light enough to be done at the edge, where resources may sometimes be limited, so that sensitive data does not leave the vehicle. To summarize, there's a need for methods to efficiently scrub personally identifying features from autonomous vehicle data, including image contents and sensor artifacts. In conclusion, the development of autonomous vehicle query systems presents challenges in data volume, bias, and privacy that aren't present in other data analytics systems. In our ongoing work, we are building new data management systems to address these problems, using a realistic open source simulator to generate datasets that let us explore these problems in depth. We are happy to share our setup with others. If you're interested in learning more, please read our paper or send an email to the address shown at the bottom of the screen. Thank you for listening.